Okay, so up next we have Derek Schulte. He is responsible for all hardware and firmware at New Matter. He works on a wide variety of projects from follicle implants to spaceflight fiber optics. He's worked on force feedback robotics, industrial scale solar trackers, and laser-initiated pyrotechnics. So can we all give a round of applause to Derek Schulte, which is...
Thank you. So I'm here to talk about efficient processing for motion control. I apologize, some of the fonts are appearing to not show up right, so you'll have some subscripts that are off. Anyway, that really boils down to how to get from A to B, and since this is Hackaday, I'm assuming that doing that along a straight line is pretty easy. But it gets quite a bit more complicated when you want to go from alpha to omega, and you're going to do that with multiple segments in 3 space, so you need to figure out how to round the corners because you don't want to come to a stop. Because we like to make stuff that looks like that. All that said, I am the principal engineer for New Matter, so I am a little bit of a corporate shill. We make a 3D printer, and it has been on the market for a little while. It's an FDM-based printer, so we're laying down basically like a robotic glue gun, strips of PLA in 50 micron to 40 micron layers with a 400 micron nozzle. I'm assuming you're all probably familiar with that process. We'll talk about a little bit about our development process, where we went from a sort of crazy, really coupled axis, but really small printer, to a pinion drive mechanism, to what we showed at CES, to a web-based system for controlling the printer, trying to sell it. Also, we can make ping pong ball launchers. It is a consumer-focused printer, so if you want to hack your printer, you're probably better off with a Lulzbot, which is one of the conference sponsors. That said, I am a corporate shill. Okay, so if you want to make a 3D printer, you first need to think a little bit about what the requirements are for that printer. Functionally speaking, you need to do spatial motion control, obviously. You've got an extruder that's going to have motion that's coupled to that spatial motion control. You have to think about thermal control for the heater. You need a path planner, which we'll talk a bit about, and obviously you need some comms on that printer. If you're building a product, there's a whole bunch of product requirements. Since this is Hackaday, I'm going to try to avoid talking about product development issues, but sometimes those work their way in. Laying out those functional requirements into a product, you come up with something that looks like a black diagram. When I do this, I highlight things in red that make you lose sleep at night, particularly connectors and harnesses. This will show up in a similar form a little bit later when we show what the firmware boils down to. When it comes time to select motion control components, often one of the first things we think of is the good old NEMA 17 stepper motor. That's not your only option. They are expensive and they can be noisy, but they're very easy to control. You can go on Hackaday and find brushless motors. You can make your own galvos, or you can machine out operable V12 model engines. If you happen to have some nice Swiss-made motors or gearboxes around, those work well too. Lots of options here for feedback and control. You might use something like a quad cell PSD, slot car motors, capacitive modular encoder systems, the Hummel solenoid, all sorts of great stuff. This is where mechanical engineers stay up late at night browsing the web. But if you're actually trying to put something together for a product, you can't necessarily go into your garage and grab that air bearing system in the lower corner. So you have to do some product engineering where you put down the parameters, you come up with a bunch of calculations, you compare those calculations against each other, put in a whole bunch of merit functions, and I'm trying to avoid talking about that. And we wound up selecting a common motor for all 4 of our axes. So it turned out that when we looked at the resolution, the speed, the force, torque, et cetera requirements, and a variety of gearing arrangements, we were able to use a common motor, which greatly helped our selection process. And in this case, it's a brushed DC motor with a high resolution encoder on the back. And that gives us a little bit less than 0.3 degrees per count in quadrature, which is very convenient. We put that together with an MXL belt drive system in the pinion rod arrangement for the X and Y axes. We used a simple gearbox for the Z axis on a threaded rod, and then a gearbox with an idler gear for the extruder, and we were ready to go. So that puts together a system. This is all of the electronics that go into a Mod T. That's it. All for $399. In that, we needed a controller board. We decided to roll our own controller board, predominantly for cost reasons, but also because we were using a servo motor system. I'm not aware of any other 3D printers on the market, at least in the sort of sub $10,000 range, that use a closed-loop control system, and that had some additional complications on the electronics that we needed to roll our own on. So we use an STM32 F103 microprocessor and Allegro A4953 motor drivers with that, and a variety of other components that are there. You always want to put in some debug functions, like having a serial port, even if you don't expose it in your product later on. We found that we actually needed 4 different voltage buses in the product, in part because of certain canned components that we wanted to use. For example, we used the CC3100 Wi-Fi module from TI, which is frankly a bit of a disaster, although it does work. And it was pre-certified. Board looks like that. You can see in the lower corner there, all of the dense stuff is the canned TI circuit area that you have to follow if you want to maintain certification. You can see the SD chip there. We've got a little SD card. And some flying leads and some connectorized stuff, which people like me lose sleep over. In the firmware, we chose to use FreeRTOS as a real-time operating system, in part to modularize the development of the code for the system. You use the GCC toolchain, ARM compiler, and the Eclipse IDE. You implement a bunch of functions. You put together a state machine. You wind up having to fake a bunch of states. You wind up having a bunch of events, and it all turns into an eye chart. And back to talking about actual path processing for motion control now that we have some hardware. So we're going to get from alpha to omega. It's not as simple as just following a simple line. We need to actually compute what these curves look like and actually get into time domain information so that, again, we can make another mess. So where does the planner fit in this process? If you're going to create something in a typical 3D printing workflow, you're going to create some geometry, whether you download that geometry or you create it or model it in a CAD package or sculpt it. You then generally export that to something like an STL or OBJ file, which is a really simplified triangular tessellation. It is then sliced in the vertical direction because we generally print layer by layer and then filled in with paths. And that creates the G-code. The G-code is basically a set of destinations and target velocities that you would like to hit in getting to those destinations. So if you want to exactly execute that line path, every time you come to a corner, you have to come to a complete stop, because in each segment of the line, you're moving at a fixed ratio between the motors. We don't want to come to a stop, in part because the flow rate, you'll have basically drool from your extruder nozzle, and it will take a long time to print. So we work on a planner. Again, this sits between the G-code and the servo execution of the actual path. And we're going from sharp corners to rounded corners. In doing this, you need to think about acceleration limits in the system, whether that be on the motor-specific side or resonant frequencies. Velocity limits in the system, you may be thinking about jerk limits, where jerk is the derivative of velocity. How much path error is permissible, how long it's going to take, how smooth you want it to be, how the axes are coupled. Dynamic computation. So a G-code file may have, say, 1 million, 2 million lines in it. Because of that, and if you're working in 96 kilobytes of RAM, you can't pre-process the whole thing very easily. So you're going to be trading off between processing that path and then kicking that path out, or kicking those instructions out to the servos. If you're going to be able to pause and resume in that system, it gets a little bit more complicated. How are you going to handle the pause and then remember where you are and then start planning again? You also need to think about how to handle interrupt discretization or residuals. If you're going to go through a sort of a fixed interval time clock on the path, the actual computed time to go through a segment or subsegment may not land or generally won't land on a specific discretization. So you need to make sure that you handle that residual so that your computed path is actually where you want it to be when it comes out. All of that said, it really boils down to how do you manage the acceleration so that you don't stall or you don't skip? How do you manage the corners so that you don't have to stop? And how you don't want to crash, because if you can only look so far ahead, how do you know that you won't be coming to a stop at a particular time? If you're not going to round the corners and you are coming to a stop, you don't have to worry about crashing. There are a bunch of ways to do planning. You can do this with really simple step functions for a lot of systems. You can use trapezoidal velocity profiles. You can do corner rounding. You can do finite jerk methods. And you can do smooth jerk or smooth jounce related methods. In the case of the Mod T, we use trapezoidal velocity profiles with corner rounding. The trick here is to keep it simple, to figure out what you can actually get away with in your system and make the early stuff work first, because chances are you may want it later during debugging. So oftentimes you'll want to work through this in a step-based fashion as your system starts to come online. Trapezoidal velocity profiles look like trapezoids. Here we have one in pink. The acceleration is a step function, the distance coming out of that. In this case, we have an S-curve, and we've capped the top of the velocity at some limit for the system. The nice thing about this is that that slope is constant. You can have a different entry velocity or exit velocity, but that slope is always constant, so it's really easy to figure out what the optimum trapezoid needs to look like. Governed by acceleration, velocity, and distance, really straightforward functions there. Very nice in that that's just a quadratic, and you have the quadratic formula, which has a discriminant that's easily evaluatable to tell you whether or not you have the roots that you want in that equation. But you have infinite jerk if your servo time is infinitely small at those acceleration transitions. So that is something that you do have to be aware of, and how your mechanism is going to handle that and how the system's going to behave. When it comes time to actually rounding the corners, again, there's lots of ways to do this. You could come to a sharp corner and come to a stop. You could implement a circular arc. You could do a spline, a track transition curve. You can do iterative breakovers. There's low-pass filter methods, all sorts of stuff like that. In the case of the Mod T, we put in a few simplifications. The first of which is that we said when we go into a corner, we're going to enter that corner at the same speed as we're going to exit the corner. We're not necessarily going to hold the same speed through the corner, but our along path, at least our along path velocity coming in will be the same as it is going out. And that greatly simplifies how you look ahead in the buffer and figure out what your the look-ahead processing needs to look like, which we'll come to in a second. We also said that we're going to have a constant per axis acceleration. So there'll be step functions in the acceleration, but you either have that acceleration or some other computed acceleration for any given subsegment of the system. We don't have a continuous function of acceleration that we're trying to evaluate. We're going to ignore what the actual path shape is as it goes through the corner. We know it's going to be bounded by a circular arc through the endpoints and the sharp corner, but we're going to ignore where it actually is, and we're going to calculate the geometry, the endpoints, the phi and rho in this chart before we do the reverse pass and velocity. And we're going to corner in the plane of phi, q, and rho, the 3 points of the start and end of the corner and the actual corner. So if you're doing this in 3 dimensions, you need to know what plane you're operating in. Once you know the per axis acceleration and velocity, the servo level target positions are trivial because we're using those really simple formulas for acceleration, velocity, and distance. A little more detail on how to actually do this. We set a limit. This is the limit that's drawn in blue here of the maximum path error if you were to use a circular arc. We calculate what those endpoints look like. The screwed up characters there are vectors for the input and output directions. That gives you the per axis accelerations. You can then inspect that against acceleration limits with your constraints from the velocity. Your velocity will also have other limits in the system, from linear acceleration and long path velocity limits. You don't want to go faster than, say, 80 millimeters per second or something like that for your extruder. And once you know those pieces of information, you have a fairly straightforward set of equations to solve for each axis. Again, they're quadratic in nature, and you know what your path looks like. One issue with this algorithm is that the velocity can be overly limited if you have a really short segment. We're going to force that corner to be less than half of the minimum segment length. When that segment length gets really small, often slicers will generate something like a 10 micron move. That can throttle the velocity down even if there isn't a big angle change that you'd like to blow through. What do the results look like? So here we have a acute and obtuse corner. You can see that with each servo cycle, we're slowing down as we come into the corner. The velocity along the corner stays relatively constant, and then we accelerate coming back out of that corner. You can see we're bounded here by the circular arcs that are shown in pink. The future stop problem is actually fairly straightforward to solve conceptually. You buffer n segments ahead, whether that's 5 segments, 3 segments, or 16 segments. You treat that buffer as the end of your path, so you're going to pretend that the velocity has to come to 0. You reverse plan to find out what the maximum speed you can reach is. And then you release the first segment, making sure that you're not going faster than that limit. You add the next segment and you loop. It seems really simple, but that actually, chances are, is going to give you a significant increase in the complexity of your firmware, particularly when you think about how are you going to pause and resume this, because now you've got a buffer that you're iterating through and rolling around in. And you need to be able to do this simultaneously with the servo loop computations, which also means that you need to have a quick calculation for your maximum segment exit speed, particularly if you use a large buffer. We use a 15-segment buffer, for example, and it seems to be plenty deep. We use feedback in our system. We have those encoders on the motors. There's a variety of different methods to do that. There are open-loop control methods, which are much simpler. You can do bang-bang and deadband control, which is what your thermostat does at home. You can do proportional control, and that can be based on position or velocity targets or some other parameter. You can do proportional integral control. When you do that, you need to watch out for what happens when you have a step change or when you're going to reset your integral buffer. You can do PID control. Watch out for servo rate and velocity resolution issues that may be available to you. We perform our servo loops at a substantially lower rate than many mechanical systems out there so that we have a better velocity resolution in our PID control. You can add in some feed-forward terms. These could be a very complicated system model of the system or simply adding in some terms that are coefficients on your target velocity or your target acceleration. You can also implement adaptive methods where you're changing the gain, say, of your PID parameters based on the performance of the system. In the case of the Mod T, we do PID with a few feed-forward terms on acceleration and velocity in the X and Y axis. And again, you want to keep it simple here. Start with something that's really simple. Work through progressive stages, and when you get something that works, you may just want to sit there and optimize it rather than getting into something really complicated or academic. With feedback, you can use that for torque utilization. In a closed-loop system, you generally need less margin in terms of the force that's available on the motors and how you're using it, because you can recover. You can use it for stall detection and motor protection, unit test, bump and drag homing. In the case of the Mod T, we sense stall in the X and Y axis on our build tray, and we sense the transverse drag in the Z-axis to home the Z-axis automatically. Because we can do that, we don't need to dial in those parameters. It's fully automatic, and it allows us to reduce our part count. We don't have any limit switches in the system. So what does this actually look like? Here's a simple star. The path is drawn in black. The execution is shown in blue. Because we have servo feedback, we can plot those servo traces If we zoom in on a corner, again, you can see this nice smooth arc that's performed there, and you can see how well we follow that. The tick marks here are 1/10 of a millimeter tick marks, so we're actually following quite well. However, this is being taken at the encoder position, not the actual tray position. If you look at a simple circle, this is just the start and the fold over on that, very similar situation. I like to look at things like what I call a bow tie path. And when I zoom in on that, it really helps you identify when you've got a problem in your path planner. You can see all sorts of strangeness going on in that path. Zoom back out, you can see in the servo plot on this, you can see we've got some resonance as we come into the center, and then it drops off as we actually execute the center. This is just a random path in space. If we look at the positions as a function of time, we have fairly smooth curves there. If we look at the velocity plots, in this case you can see we have, it's basically all lines, and it should be because we're using constant acceleration, which gives us these trapezoidal or linear velocity profiles. They're capped at our maximum velocity. The combined velocity is in red there. You see little dips occasionally. For instance, in the top center, that's actually when we're going through a corner. I said that the entry and exit velocity are the same, but the along path velocity through that corner actually dips a little bit. You can then plot the acceleration. In this case, we have a 500 millimeter per second squared acceleration cap, and you can see how that's implemented. There are 6 spots there where we exceed that, and that's where we're playing a little bit of dirty math to deal with handling of small segments. And then we can go back and put those servo traces on the path and actually look at the error as a function of time. The tick marks here are 50 microns apart. It's about half a hair apart. The total size is the size of the nozzle diameter, so it tracks fairly well. So we've talked about how to get from alpha to omega with the mod T. We do this with the high-resolution encoder. That's 334 lines going around. We do that with a little bit of math. And thank you, Hackaday, for having me to come, and enjoy your time at SuperConference.